All right, so this is the SafePKT project. To start off, what is Packet? Packet is a project to amateurize the operation of last mile internet infrastructure. Does that mean you would put a device in your window, outside on your roof, whatever, and you would be sharing internet with your neighbors? The tech is not all finished yet because it's fairly complicated, but this is what we're working on. And the idea is that you would be selling, your device will be automatically selling tokenized bandwidth leases. So to break that down, a bandwidth lease is the right to use a certain amount of bandwidth between point A and point B over a certain amount of time. So once that's tokenized, you can kind of think of it like an NFT that gives you a right to access that lease. Then the aggregators, which are like VPN companies, will go around and buy these leases in order to be able to provide a better service to their customers, because they provide, well, the ability to reach the internet without already having the internet, which if you're a VPN provider, that's a better service. The problem with this is that token issuance is really expensive. I looked up some statistics and I found that issuing an NFT on Ethereum chain can even cost as much as 1,000 euros worth of gas fees, which are the transaction fees, because Ethereum is decentralized, but it's still kind of centralized in that everything has to go through the Ethereum chain. This cost, it's kind of a disaster for bandwidth tokenization because it just makes it impossible to tokenize something that's worth maybe only a few cents or even should be almost free. We are working on a project in the ecosystem called Token Strike. It is a very simple idea, and it just allows everybody to issue their own tokens, and each token is issued on its own sovereign chain, so you don't have any fees. But when you're doing tokens, you're doing smart contracts, and smart contracts are difficult to get right, and if you get them wrong, you can have a lot of problems. SafePKT comes in and helps us to verify these smart contracts. So a smart contract that's written in parity text Inc language, that's a variant of Rust, can be automatically verified. And we use symbolic execution to test the possibilities which would not be covered by a normal test. The architecture, so we have a front end, we have a command line app, we have a Visual Studio Code front end, and we have, of course, the back end, which runs on a server, and that does the actual compute. So I'm sure you're not here for these beautiful slides, although they are incredibly beautiful. Thank you to Matthias for that. What you're really here for is the demo. So right here I have a smart contract, and as I put in a bold letters here, this smart contract has a bug. It's a very, very nasty bug that can cause you to print money. And I'll point out where the bug is to you guys. The bug is in transfer, and the problem is that it's taking a signed value instead of an unsigned value. And so if you pass it a negative value, it's going to allow you to not only just take money back from somebody else, but actually to cause a rollover and then get infinite money. Really disastrous. We have, as we're good programmers here, we wrote a test on our smart contract to make sure that we can transfer some tokens with this smart contract. But instead of just saying that we're going to transfer, say, 5 tokens or something, we set a symbolic number here. And when we're just doing regular testing, that number is going to be the default, which is 1. But when we're testing in the SafePKT environment, it will be a symbolic number that is anything between -5 and 5. So I'm going to show you that when we run the test, we can run this test here and it passes. It seems like it's all right. But if we do SafePKT analyze, then we're going to be uploading this source to the server, which is going to do the actual verification. And then the server is going to start. And now it's compiling this code on the server side in a special form, which will be used with the CLI verifier. And then once it's compiled that, then it's going to perform what's known as a symbolic execution. And it's going to be using this value that is anything between -5 and 5. And by having this number that isn't really pinned down, we're going to identify the actual problem with this smart contract, and we should expect in a few minutes to have a test failure when we wouldn't have if we were just testing with regular numbers. So this is a little bit like what you might expect from, say, a fuzz testing where you're inputting random numbers, but whereas fuzz testing, you're kind of just putting random numbers. With this, you're putting a symbolic number, so you can trust it a little bit more regular fuzz testing because you know that you explored that entire range, although the entire range is relatively small. small. So here we actually have the error, librs 176, and that's our assert that failed. And there it is on 176. We see that Alice actually has more than 100 tokens, even though there was only ever 100 tokens issued to begin with. And so that's very wrong. What happened was the negative number got cast into a positive number and it became gajillions. We also have the ability to run this test here in our editor. So if you're not wanting to jump into the command line just to do a little test, then you can just run it right in the Visual Studio Code editor, because we have the SafePKT extension right here, and this is something that anybody can just install right in Visual Studio Code without any problem. As far as the repositories, there's our failure. We have our buggy smart contract, which has been uploaded, and we have and this buggy smart contract can also be used as a base for developing non-buggy smart contracts, because it has all the infrastructure that you'd need to write a Polkadot style safe smart contract. We also have, of course, the back end, the front end. We have the website for safePKT.cjdns.fr, and that we showed in our last demo, so I won't get into that, but it still works as it did before.